Okay, so this week we are going to learn how to evaluate the F ratio. So in class last week, we went through the steps for actually calculating the F ratio. We went through the basic ratios, the sums of squares, the degrees of freedom, the mean squares, and finally we got to the F. We put it all together in a ANOVA summary table, and now the question is, what does that F ratio mean? How is it that we can look at the size of the F ratio and determine whether you have something going on in your study, whether, for example, noise affects memory or not. In order to do that, we have to talk about something called the theoretical sampling distribution of F. So I'm going to start off right away by saying that this is probably the most complicated thing I'm going to talk about all semester. I'm going to go through and explain what I mean by this. We're going to go through the logic of it, but I will tell you that in spite of this kind of very abstract slide and very abstract things I'm about to talk about, the process of evaluating the F ratio is actually really simple in practice. All right, so we're going to start with the reason why we do it, the theory behind it, and then I will, in the next video, show you practically how it is that we go through the process of doing this. All right, so we're going to start up here. Recall in our last video, we talked about the null and the alternative hypotheses. And remember, the null hypothesis is the one that says there's nothing going on. So the null hypothesis says things like there is no treatment effect, the means are equal, mu1 equals mu2. This curve here that I've drawn is the theoretical sampling distribution of F when the null hypothesis is true. All right, so what does that mean exactly? Basically, this curve represents the likelihood that we will obtain a given F ratio by chance. Another way of thinking about that is it's the likelihood that we'll obtain a given F ratio in error when the null hypothesis is actually true. All right, so just by chance, if we were to just, randomly generate numbers, this is the likelihood that we would obtain just by chance an F ratio of this size. Now, look at this curve. You can see, first of all, let's look at the axes. So the horizontal axis is the possible values of F ranging from 0 to infinity. Obviously, it's not to scale. And the vertical axis depends on where you look at it. Sometimes it's they put it in frequency, sometimes they put it in probability. Either way, it's going to start at 0. I usually don't put the upper axis label on here because it depends. If it's frequency, it's going to be infinity. If it's probability, it's going to be 1. Just know that it starts at 0. So this curve represents the possible values of F when the null hypothesis is true. So if you notice, most of the area under this curve, right? So most of the area under this curve is with low values of F. So when the null hypothesis is true, we expect low values of F. When the null hypothesis is true, we expect low values of F. Let's think about what that means. When the null hypothesis is true, it means there's no treatment effect, it means there's nothing going on, and we expect low values of F. So if we think about this another way, when we obtain in our study high values of F, that's probably a good sign that the null hypothesis is not true or that the null hypothesis is false. All right, so again, I know this is super abstract. I don't want anybody to stress out about the abstract level of this because, again, I'm going to really break this down into brass tacks. It's going to be super easy. But basically what I'm trying to say with this chart is when you obtain a low F ratio, a small number, 0, 1, 2, when you obtain or when you calculate a small f, that's probably a good sign that the null hypothesis is true, which is just another way of saying there's nothing going on. And when you obtain a high value of F, it's probably a good sign that your null hypothesis is false and that there is something going on. All right, so just kind of a little bit more on this. So again, this curve represents the likelihood that we're going to attain a given value of F by chance when the null hypothesis is actually true. But if we think about this from a research perspective, we don't want to find things by chance. We want to be confident that we obtained our results for real, not in error. So we want to be confident that our results were not likely to have found in error or by chance. So basically what we're going to do is first, we are going to establish for ourselves what likelihood of error we are willing to accept in a study. Now, again, I'm kind of I'm tying this in with a lot of things that we've talked about so far this semester. So remember, I told you there's always error. And error can come in the form of measurement error, it can come in the form of variation in testing, it can come in the form of individual differences, but there's always error. We know that for a fact. So we have to ask ourselves as researchers, what chance of error are we willing to accept? We know there's going to be error, but how much error are we willing to accept? And basically in psychology, we are usually willing to accept a 5% chance of error. That's basically what we're willing to accept in psychology. So 5% chance of error. And what that really means, and this is something that might make sense to you from a previous stats class, is when we have a 5% chance of error, this means we have 95% confidence. All right, so there's a relationship between error and confidence. Whatever our confidence is, our error is 100% minus that. So for 95% confidence, we've got a 5% chance of error. If we have a 1% chance of error, that means we have 95% confidence. All right, so again, super abstract. I know I'm kind of all over the place here, but the point is we're going to use this curve to establish a minimum value of F that we are willing to accept as evidence of treatment effects. So basically what we're going to do is we are going to establish a cutoff. All right, and right now this is abstract, but in the next video you'll see that it's not abstract at all. It's actually very black and white. We are going to use this curve to establish a cutoff. This is going to be the minimum value of F that we are willing to accept as evidence of treatment effects. And we don't just randomly choose this cutoff. This cutoff is chosen as the point where only 5% of the values of F are above the cutoff because of our 5% chance of error, and 95% of the values of F are on the other side of the cutoff. All right, so I'm going to go into this a little more detail in the next video, and then hopefully in the next video, if not one more, I will show you exactly how we're going to use this practically. But again, just kind of an overview of what we're talking about here. This is a theoretical sampling distribution of F, represents the state of the world when the null hypothesis is true, and we are going to use this to evaluate our F ratios.